ask that if a graph is a subgraph of another graph, then is it a minor? If y is a subgraph of x, then is it a minor? You can't answer it quickly? Subgraph notation is this. I am asking this question. If y is a subgraph of x, then is y a minor of x? According to our definition of a.
Yes.
Yes, very good. Because
We take y is equal to z.
yeah, y is equal to z, and it's a subgraph. Identity is a subgraph. So y is a subgraph of x, which means there's a subgraph inclusion there. And then y, or whatever is the identity mapping, is a contraction. How do you understand that? Identity mapping is a contraction. Every part, if we partition the vertex, every part is single vertex, which is technically connected. So this is a contraction, no problem. Identity is a contraction. Therefore, by our definition, this is a minor inclusion. This commutative diagram itself is a proof of this statement. 2. If f is a contraction mapping from x to y, is a contraction mapping. Actually, I have omitted quite a lot after the definition of contraction mapping, because you can define a graph even without having y first. After partition, you just use the part, each part of the vertex and define a graph very easily. And that's what we're talking. If this is a contraction mapping, then we are asking, is y a minor of x? Dr. Farooq will instantly tell you it is. Now what is happening? So this is a contraction mapping. We put that contraction mapping there. This is f. This is given, right? And now that you need to put x there, but between x and x there is an identity mapping, which is subgraph inclusion. This time, what I said was correct. What I said last time. There exists contraction mapping because it was given. There exists an identity map which is subgraph inclusion. Every graph is a subgraph of itself. Whatever set doesn't matter. So there is by our definition, there is a minor inclusion. Y is a minor of x. These two seems to be zero, right? We are still not standing up. We are lying on the ground. We have not even lifted ourselves 1 millimeter on top of that. So it's very safe because we are simply copying this definition, our own definition. And we get this easy, what I'm saying. But this easy observation gives you something. What is it? Let us rephrase it. First example said that every subgraph is a minor. Second example said that every contraction graph is a minor. So minor is a common generalization of the concepts of subgraph inclusion and contraction mapping.
Yes.
This is very strong conclusion from this easy. So the concept of minor is common generalization. Is a common generalization of the concepts of subgraph inclusion. English language is too long. Probably Urdu is shorter than this. Because Urdu for mathematics is much shorter than mathematics. Because I accidentally asked someone, Riyazi is mathematics, which has only 2 syllables, even if you pronounce a Z. But mathematics, 4. And it is not English, because it came from ancient Greek language. Urdu is Urdu. Or maybe it has some origin in Arabic. So I think in this case, Urdu is better. This generalization is too long. Generalization. Or let us drop the concept of the subgraph inclusion. And contraction. Even with these two diagrams, which is almost nothing, we have this conclusion. Now let us see some familiar graph again. So let us have a look at, and now we will get for some. There's a graph called Peterson graph. Peterson's graph, which was when Julius Peterson first published his paper in 19th century. This graph was given as a counterexample to some question he considered in quadratic forms. You have to know this. You go back and check. So how important this is going in linear algebra, and we're going to encounter several more examples in the linear course where graph theory is going back to the mathematics. And the Peterson graph, P is usually denoted by P, and then it is 10 vertices. Let me draw it nicely. I have beautiful drawings of this in my computer, but if I go there, we waste time. The outside is a circuit of length 5. It doesn't matter, we don't call it outside, because in graph there is no up or down or upside. This is only which vertices are adjacent, which are not really important. And then I'm going to draw the other 5 edges in red. You assume that this is red. Now those 5, the end vertices, pairs of end vertices of each of those 5 edges, red edges, induces a connected subgraph, which is K2. So this partition of 10 vertices into 5 sets is a partition satisfying our condition for the contraction. So this gives a contraction, and the contracted graph, where the red edges are all become vertices. 1, these are actually red. 2, 3, 4, 5. Outside circuit is still there. Inside circuit is still there. Only 5 edges which are contracted are those 5. So this is a contraction. Therefore, this is K5. Therefore, K5 is a minor of the Peterson graph. If you want to prove this using the old definitions, how difficult it will become, you have to be careful. If you use this commutative diagram over there, my definition, that is, it becomes just a graph you display and then you get the understanding. Of course, the commutative diagram is equivalent to the famous people's concept. Now, I would like to draw a graph. Clever students should really answer my question after I finish drawing this. I have seen some clever students already. I hope I get it correct, but I don't. These things cannot be memorized. This is a graph. It seems that it has 10 vertices because 1, 2, 3, 4, 6 plus 3 is 9, plus that one is 10. And every vertex is still degree 3. But it looks very different from that graph. First question is, are these two graphs isomorphic? It needs some work to understanding. But let us do it together. What is your guess? Are these two graphs isomorphic or not? This is not democratic election. We don't like democratic election in mathematics. Sorry, Mr. Trump.
Yeah, it seems.
Yes, I think you see some. So let us give names to the vertices. Let us say this is 0,
Yep.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. Right?
Yes.
Now I see a circuit of length 5 with 0, 1, 2, 3, 4. Let us find the circuit of length 5 and make it 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. This is a circuit of length 5, right? Now, what is the only other neighbor of 0? Only other neighbor of 0 is 5. 5 sits in the middle. Only other neighbor of 1 is 6. Where is this? Only other neighbor of 2 is 7. Where is 2? This is 7. And we have to verify that those 5, 7, 9, 6, 8, 5 is a circuit of length 5, and then we finish the isomorphism. We realize the isomorphism immediately. Now, only other neighbor of
8, 9.
how did you
7
get?
to 9.
Of 5 is?
We get
We get 5.
7 from 2.
7 to 9.
I think we made some mistakes somewhere already. Let me restart. So we first given name to these 5 vertices as 0, 1, 2, 3, 4. So those 5 edges are already there. Now we look at the only other neighbor of 0 is 5. The only other neighbor is this one. 5 is correct. 2, 1 and 4 are its neighbor. This 5 is correct. Only other neighbor of 1 is 6. Where is 1? Only other neighbor of 1 is 6. Now only other neighbor of 2 is 7. Where is 2? This is 7. The only other neighbor of 3 is 8. The only other neighbor of 4 is 9. Now we need to verify that 5, 7, 9, 6, 8, 5. Well, it is right. 5, 7, 9, 6, 8, 5 is a circuit of length 5 here. Let us have a look at it. 5, 7, 9, 6, 8, 5. This is a circuit of length 5.
Yes, sir.
You see how another way of looking at this is if you take this vertex down outside and then you swap these two and put it there, and then you have this upside down.
Yes.
If you have one of the apps we designed, you can quickly verify that these two graphs are isomorphic. So this is also Peterson graph. This is also Peterson graph. Now we erase. Have you taken the picture yet?
Yes.
We erase the numbers because numbers are only
For understand.
given names for our own convenience. It doesn't have anything to do with the graph actually, or it has something to do, but for us to realize that this is an isomorphism, I'm going to erase the numbers and then call vertex 5x. Okay now, right? The blackboard is very good because we can really erase out the two things. We call this x, and then we look at p minus x. You remove or you delete the vertex x and its incident edges. So there are 3 edges which are gone. So after you delete x, these 3 edges are gone. So you will have 3 new vertices of degree 2 each. And I am going to, in that remaining graph, these are gone. I will slash it. In the remaining graph, we look at these 2 edges. Their end points are pairs of elements in the partition, and all other vertices are single vertices. X is gone already. If you contract that, what do you have? Oh, another one. If you contract also this one. If you contract that, if you have deleted that one, if you contract this one, these two will be joined by an edge. Contracted that one, these two will be joined by an edge. Contracted this one, these two will be joined by this edge. So we now draw that graph. It is the outside circuit of length 6 is still there. And these edges are new. What is this graph? Some people might recognize, but I want you to really think. Can you identify that graph? Eh?
If there is an edge between, then it's a wheel.
No, it's not a wheel. This is the complete bipartite graph K33. Let me prove it now. 3 parts are, I'm not coloring. I'm coloring the vertices of the other 3, the other part in red. You need to verify that there is no edge between any 2 red vertices and there is no edge between any 2 white vertices. There is an edge between every red vertex to every white vertex. And each color, the red and white are exactly 3 each. So it's a complete bipartite graph. If you have a partition of 6 into 3 sets, or 3 sets, and then you introduce all the possible edges between, we see that it's a complete bipartite. So this graph is isomorphic after contraction. 3 edges E, D, E, F. It becomes that one. What did we prove? We have just proved that you know that P minus X, there is a subgraph inclusion eta from because only 1 vertex and 3 edges are missing, so it's a subgraph. And we have just constructed a contraction F of this crazy. Therefore, by our definition, there is a binary equation. These seem like just individual, very silly and easy examples to you because we now have the advantage of a good definition, a good concept. Before, prior to that, this commutative diagram, it was utterly more horrible than this. And now it's become beautiful. Without this, it will be not beautiful. Without that diagram. Not only so, we have proved that this conclusion, K5 and K33 are both minors of the Peterson graph. Not only so, there is a contraction from P to K33. This should give you some hint to ask a few very interesting questions, which are hot subjects in graph theory, finite graph theory, and we're not restricted to finite. These definitions, it doesn't depend on graph is finite or not. It depends probably just on unbelief. There are two conclusions we have just deduced. One is this one. Peterson graph has both K5 and K33 as minors. And 2, there is a contraction mapping from Peterson. No, this is K5, I'm sorry. Then it would be, this is the false actually, you should really prove this is false. There is a contraction mapping, this is a contraction mapping FA from P to K5. For those who study the beginning graph theory, you realize that K33 and K5 are characteristic to Euclidean plane. It is a topological characterization of the Euclidean plane given by Grotowski in 1927. And we asked this question and gave hint to some of the interviewees. She wasn't able to answer anything at all, even didn't know what the planar graph was. So this is not only a characterization, the Grotowski's theorem is not only a characterization of planar graphs, it is actually a topological characterization of the Euclidean plane. That is the importance of that theorem. We don't include that Grotowski's theorem in here because it's not our concern in this mini course. It proves that the Euclidean plane, the surface is Euclidean plane if and only it doesn't contain K5 or K3. It actually says that. Not only the graph is not planar if and only if it contains one of them as a minor. This is an observation which comes out from this. Any questions you may want to ask here? And there are lots of something like 200, 300 papers in GCTP, Journal of Combinatorial Stability, which is we consider as top. I never published in the top journal in our subject, in graph theory and combinatorics. There are lots and lots of activity there concerning a question which we can derive from this. This seems that Peterson graph contains both these minors. First of all, this is what we deduce. Now, you might ask if you're given any graph, if it doesn't contain this one, you ask that, does it also not contain that one? This is kind of question. Or otherwise, if it doesn't contain this one, it doesn't contain that one? These questions are not well answered yet. So the activity is very much. So some questions are like this. Because Grotowski's theorem characterized planar graphs, finite undirected planar graphs. So the question was, can a planar graph, it will contain either, it will contain K5 minor or K33 minor. But can a planar graph only is necessary to contain one of them? It's only necessary to contain one of them, non-planar graph. That was a huge question which has been studied in graph theory, and we were not concerned about this in this. So, I now forgot because I'm carried away too far away from the mini course. We are in graph theory quite a lot swimming. Another thing, which minors are necessarily not contractions? That's another question you can derive from this. For example, that minor, is it a contraction for is P33 a contraction of Peterson graph? So the question is here, exercise. Okay. Exercise question. Is there a contraction? You need to prove it. F from Peterson graph to P33. If there is, you need to prove it. Keep the partition and then verify that every part induces a connected subgraph. Or if it is not, then you are in a big trouble because you have to really consider all mappings, all partitions, and then you know how many partitions are there of 10, set of 10 points, 10 vertices, 10 elements in it. You consider all partitions and then prove that each one of them does not give you a contraction. Of course, you can take shortcut and do it better. By looking at the number of vertices. Peterson graph has 10 vertices, right? P33 has 6 vertices. So how many edges are going to be contracted? Every contraction of every one edge will reduce the number of vertices by 1. So you're going to contract 4 edges. And you look at whether these 4 edges can be independent in Peterson graph. You can't, because if you take that one, if you take this one, and that one is independent, and that one, then another edge cannot be independent with the other. So it should be something like 2 edges are adjacent, and then you need to consider all the cases. And then in each case, the contraction of those edges cannot yield K3D. Then you prove that it is not, there is no such contraction. If you say that there is a contraction, its proof could be easy. Just to produce one partition and verify that that partition satisfies our condition. So this is one exercise question. We should do this because this is graph theory question. Okay. Now, second exercise question. One. Minor inclusion is a binary relation among graphs, among undirected graphs. It doesn't have to be finite. So let us say that if Z is a minor of Y and Y is a minor of X, then does this mean that Z is also a minor of X? If it is, then you need to prove. If not, then you need to produce an example. Now I need to move to the next. I suddenly remembered what it is. So next section. Any questions about those questions? You can ask them. You should really do this, even if you are unstudied graph theory, because we have all the concepts already done here. So it can be done if you understood the concepts. Another way of saying this is the binary relation of minor inclusion transitive, we are saying.
Yes.
Thank you. Any comments or questions? Seems everybody is quite awake. In South Africa, by this time, 1/3 of the students would have been deeply in sleep. Because they eat too much meat and it's all very fat, so it's very easy to fall asleep. Okay, that's fine. I'm not insulting them. I like them very much, by the way. So next, we have just dealt with graph morphisms. Graph morphism means there is something which I have to chat here. If you studied category theory, such as Professor McRae's categories for the working mathematician, you will have found already that for mathematical objects categories, there aren't too many different morphisms, which consequently, which also implies that there aren't too many concepts of products. For example, category of sets, there's only one product, Cartesian product, which is a categorical. And you have, when we're talking about product, we need to talk about categorical products. Of course, you can form other products, but they aren't categorical. For groups, essentially there's one type of morphism, group homomorphisms. Abelian groups, the same story. Now, when you talk about categories of graphs, even undirected graphs, you can even impose an extra condition of finite undirected graphs. There are lots and lots of different categories, depending on the morphism you take. So you could take homomorphism as morphism, you could take contraction as morphism, you could take comorphism as morphism. For each one of these type of morphisms in the category, you have a special type of categorical product. You may or may not have it. So for graphs, the category of graphs, mathematical objects called graphs, is, even finite undirected graphs, has much more information than other mathematical categories. Probably almost as rich as a category of topological spaces under the morphism of continuous matrices. So we now want to define graph products. And then also need to mention categories. We are going to only introduce two major graph products, which definitely give different categories. Using morphism, which in one case is a homomorphism, in the other it is contraction matrix. Oh, of course, there are lots of other products and other morphisms, other categories of graphs. We are not going to worry about it because we are going to use the two products later on. So we are only worried about that. So we will. I'm not even using the categorical notation, because every time when we see a category, we give the full name in words. So don't worry about that. We will define the product. So product 1, I'm not going to say the words, I'm going to do some deduction, and then after that I name them. When you have a child born today, his grandfather, parents would be very anxious to quickly give a name, and because now he's born, he or she is born. And if you're in a haste and you give a name, the name turned out to be not a nice name. And then this child will suffer when he grows up. There are names like snake or dogs can't eat. In many languages, they are there. Even dogs can't eat him because his 2, 3 older brothers died as soon as they were born. So black people did, oh no, we give this name, this child trash, so that nobody can take it. Or dogs can't eat. So they give this kind of name. So we shouldn't be hurrying. We deduce it, and then we convince ourselves that this name is good. And then we give it. Because we're not worried about their growing old, because mathematics, they're there all the time. So let's not talk about it. One product we denoted by